Welcome to the Deep Dive. You know, the show where we try to cut through the noise and bring you some surprising, maybe actionable insights. Today, we're plunging into a world you can't actually see, but it powers so much of what we rely on, like every single day. We're talking about that incredibly small, yet, profoundly powerful boundary where chemistry and electricity fundamentally meet.
It's such a foundational space, truly, an invisible interface, really, where these transformations happen right down at the atomic scale. But the implications are just vast, touching everything from how we store energy in batteries to, say, how we stop metals from corroding.
Exactly. And our mission for this deep dive is to, give you a bit of a shortcut to really understanding how these electrochemical systems actually operate. We're going to unpack the essential building blocks, starting right from that literal interface where all the action happens, and then move all the way to the frankly ingenious ways scientists have figured out how to make incredibly precise measurements in this microscopic realm.
Yeah, and we'll do that by drawing from expert insights into these electrolyte interfaces. Yeah. And also the critical need for three electrode systems, which we'll get into. And those often overlooked sort of silent contributors. Yeah. The supporting electrolytes, really a journey into the remarkable precision that underpins this whole field.
Okay, so let's start right at ground zero then. The heart of it all, the electrochemical double layer where worlds collide. What actually happens, like the very instant you dip a metal electrode into a liquid electrolyte solution? It can't just sit there, can it?
No, you're right. It's far from simple.
Yeah.
It's actually fascinating. The moment that metal surface touches the liquid, there's an immediate natural attraction. Ions that are already in that liquid electrolyte, they get powerfully drawn to the metal surface. They don't just randomly float by. They actually start to absorb, basically stick onto it, forming this highly organized arrangement, like a microscopic ordered dance party right at the surface.
Huh. I like that. An ordered dance party. And it's not just one layer of ions sticking, right? That's where the double layer comes in. Can you unpack that structure for us?
Precisely. So the first part of this double layer involves ions that absorb directly onto the metal. They often have to shed most of their surrounding water molecules to get really, really close. And this forms a very dense, very ordered sheet that we call the inner Helmholtz plane, or IHP for short.
Okay, the IHP, like the dancers right up against the stage, as you said.
Exactly. Tightly packed.
So if that first layer happens to be, let's say, negative ions, what happens next to make it a double?
Well, that concentrated negative charge in the IHP naturally pulls in ions of the opposite charge from the bulk solution. So positive ions in this case. These counterions then gather nearby to sort of neutralize that initial layer, and they form a second, slightly more diffuse layer. The second layer can include what's sometimes called the outer Helmholtz plane, where you have solvated ions still with their water shells just outside the IHP. So you end up with these opposing polarities, positive and negative charges, separated by an incredibly tiny distance right there at the electrode surface.
And that structure, separated charges across a tiny gap, that immediately sounds like something from electronics, doesn't it? A capacitor.
Absolutely. That's exactly what it is. It's the very definition of a capacitor. And that's why we call it the double layer capacitor, CDL. The scale here is just, mind-bogglingly small. We're talking a distance of roughly 1 nanometer, sometimes even less.
1 nanometer. That's, 10 hydrogen atoms lined up? So what kind of capacitance are we talking about for something that tiny?
It's incredibly small. But the capacitance values are surprisingly high, typically around 10 to 30 microfarads per square centimeter of electrode area.
Wow.
And think about the electric field across that tiny gap. If you apply just 1 volt across 1 nanometer, the electric field strength is absolutely immense. It works out to 1 gigavolt per meter. That's 1 billion volts per meter.
1 billion volts per meter. That's staggering.
It is. It's the kind of intense force that can literally rip molecules apart or drive incredibly specific, fast reactions right at the atomic level.
Yeah.
It's really where chemistry becomes electricity, right in that tiny zone.
That's an incredible amount of force in such a microscopic space. But is the double layer always that tightly packed, just 1 nanometer, or does it vary?
That's a great question. And our understanding has evolved there. That ideal model assumes that super tight packing, but real-world conditions, they vary. What if the solution is really dilute, like hardly any ions? That's where models like the Gooey-Chapman model came into play. This model suggested that at low electrolyte concentrations, maybe around 1 millimolar, the charge distribution might spread out over a larger distance, maybe 10 nanometers or so. It's more diffuse, the ions have more room.
Okay, so like a spread out cloud of charge instead of a neat sheet. And then is there a model that kind of brings these ideas together?
Exactly. The Stern model is sort of the synthesis of these ideas. It's quite clever. It acknowledges that, yeah, at higher concentrations, say 1 molar, you definitely still have that very tightly packed inner Helmholtz plane right at the electrode. But then it also incorporates the more diffuse distribution, like the Gaia-Chapman idea, for the charges that are a bit further out. It gives us a much more complete and, frankly, more accurate picture of how these double layers actually behave under different conditions.
Okay, that makes sense. So this double layer capacitor, the CDL, it accounts for current that passes without any chemical reaction actually happening, right? It's just charging and discharging this tiny capacitor.
Correct. That's non-Faradaic current.
But what happens if a chemical reaction is occurring at the surface? Involving electrons actually being transferred.
That's the crucial difference. When an electrochemical reaction does happen, meaning a real chemical change, like a molecule gaining or losing an electron, maybe metal dissolving or plating out that process, generates its own current. And this current is associated with something we call Faradaic impedance, often written as ZF. It basically represents the resistance to that chemical transformation and the electron transfer step itself.
Faradaic impedance, named after Michael Faraday, I assume, pioneer in this area?
The very same. His work laid so much groundwork.
So if a reaction is happening, how do we then model the electrode's electrical behavior?
In that case, a single electrode interface can be modeled pretty accurately as this double-layer capacitor CDL, acting in parallel with this Faradaic impedance ZF.
In parallel.
Okay. Yeah, think of it like an electrical circuit with two parallel paths or branches. One path is for that capacitive current charging the double layer, no chemistry. The other path, in parallel, is for the Faradaic current, where the actual chemical reaction and electron transfer are taking place.
That model seems really intuitive. But, okay, here's where it starts to get tricky, I imagine. Once you appreciate how complex that little interface is, you realize how hard it must be to actually measure what's going on there precisely. Which brings us to a really fundamental problem, especially for anyone new to electrochemistry. The two-electrode problem, why simplicity fails. I mean, if you just want to do a basic experiment, you need at least 2 electrodes to make a circuit, don't you?
Absolutely. Minimum of 2. You need 2 points to complete the circuit, let current flow, and establish some kind of potential difference you want to measure or control.
But then, bam, you hit this fundamental wall. You can't just stick a voltmeter probe into the solution and measure the absolute potential of just one of those electrodes. Why not?
Yeah, this really gets to the heart of how we define and measure potential here. The core issue is, simply put, you cannot measure the absolute potential of a single electrode. You just can't. The moment you try to measure it with any kind of probe, like a multimeter lead, that probe itself becomes a second electrode where it touches the liquid. And just like your main electrode, it instantly forms its own electrochemical double layer.
Okay. So you're not actually measuring the potential of the electrode you care about. You're measuring a difference between 2 potentials, and both of them are kind of unknown.
Exactly right. If the potential drop across your working electrode interface is X, that's what you want to know. And the drop across your probe's interface is Y, all your instrument reads is X minus Y. And the real kicker is that Y value from your probe.
Mm-hmm.
It's often comparable in size to X. It's definitely not negligible.
Yeah.
So you're always measuring a difference between 2 unknowns. You can't isolate the X you're actually interested in.
Wow. It's like trying to measure the height of one person when they're both standing on wobbly platforms of unknown height.
That's a pretty good analogy, actually.
Okay, that's a serious limitation. But you said it gets even trickier.
It does. Even if you apply a known voltage across your simple 2-electrode system using a power supply, there is absolutely no guarantee how that total voltage splits itself between the 2 electrode interfaces.
Right. So you apply, say, 1 volt total. You can't assume it's 0.5 volts at one electrode and 0.5 at the other.
Not at all. That's just intuition, but it's usually wrong. The potential drop might be, for example, 0.8 volts across the interface of your first electrode and maybe minus 0.2 volts across the second one relative to the solution potential somewhere in between. The total difference is 1 volt, sure, but how it's distributed across each interface, that's completely unpredictable and depends on the specific kinetics and conditions at each electrode.
So you don't know the split. And then if you change that applied voltage, let's say you bump it up from 1 volt to 1.5 volts, you also can't tell if that extra 0.5 volts is shared evenly, or if one electrode interface takes most of the change.
Precisely. You have absolutely no way of knowing or guaranteeing how that change distributes. Maybe the first electrode's potential goes from 0.8 to 1.1 volts, a 0.3 volt change, while the second one goes from -0.2 to -0.4 volts, a -0.2 volt change. The total change is 0.5, but it wasn't split evenly. Or maybe the first electrode barely budges, going from 0.8 to 0.9, while the second one takes almost all the change, dropping from negative 0.2 down to negative 0.6. There are countless possibilities, and you're essentially flying blind regarding the potential at each specific interface.
Which means, okay, if you're trying to study a specific reaction happening at one of those electrodes, your main electrode of interest, and you see the current change when you change the voltage, you have no confident way to link that current change to a specific potential change right at that electrode's interface.
Exactly. It makes interpreting your results incredibly difficult, if not downright impossible.
It seems like it would completely undermine any attempt at quantitative analysis.
It does. You can measure current, you can apply voltage, but you can't truly understand or isolate what's happening at the interface you care about. It's like trying to tune a multi-cylinder engine, but you can only measure the total RPM, not the contribution of each cylinder. You don't know where the problem or the improvement is really coming from.
Okay, so this seems like a massive roadblock. How on earth do electrochemists get around this fundamental measurement problem? This must be where the ingenuity you mentioned earlier comes in. Which brings us to the three-electrode solution and the role of supporting electrolytes. This is the standard approach, right?
Absolutely. This is the breakthrough. The three-electrode system is pretty much the undisputed standard now for getting precise, meaningful electrochemical measurements. And the key addition, the magic ingredient, is the reference electrode.
A reference electrode? What makes it so special? How does it solve that core problem of not knowing the potential distribution?
Its unique and totally critical property is that its potential drop across its own interface, its own metal-liquid boundary, is designed to be constant and stable. It doesn't change during the experiment. Now, we still can't know its absolute potential value, just like before, but the power comes from knowing that whatever its potential is, it stays put. It doesn't drift or change.
Ah, okay. So because its potential is fixed, any change in the voltage you apply between this stable reference electrode and your electrode of interest, which I think you call the working electrode.
That's right. The working electrode is the one you're studying.
So any change in voltage between the reference and working must occur only at the working electrode's interface.
Precisely. You've nailed the core insight. Because the reference potential is stable, any voltage you apply or change between it and the working electrode effectively gets forced to appear only across the working electrode's interface. This is hugely powerful. It means you can now directly link changes in current to specific known changes in potential at the working electrode. Yeah. Suddenly, your experimental results become interpretable, quantitative. And this is why, if you look at any published electrochemical paper, the potentials are always reported with respect to a specific reference electrode.
What are some common ones people might hear about?
Oh, common ones in labs are the standard hydrogen electrode, or HEE, that's the theoretical baseline. More practically, you see the standard calomel electrode, SCE, a lot, and especially silver chloride, NgEgCl electrodes. They're robust and reliable.
Got it. Now, practically speaking, I've sometimes seen setups with something called a Lugin capillary. What's that doing there?
Yes, the Lugin capillary. It's a neat little piece of glassware, usually. It's designed to minimize the effect of solution resistance between the working and reference electrodes. Basically, it allows the sensing tip of the reference electrode to be placed extremely close, like almost touching the surface of the working electrode. This ensures that the potential difference being measured and controlled is truly the potential right at the interface you care about, not some potential drop across the bulk solutions sitting between the electrodes. It improves accuracy, especially in solutions that aren't superconductive.
Okay, helps keep the measurement really focused on the interface. Makes sense. But hang on, thinking about the reference electrode again. If it needs such a constant potential, what stops current from flowing through it? If significant current went through the reference, wouldn't that mess up its potential and defeat the whole purpose?
That is an excellent point. And you've just reasoned your way to why we need the third electrode.
Yeah.
You're absolutely right. If any significant current were forced through that delicate reference electrode, its potential would shift due to polarization effects. It would stop being a reliable reference. And that's exactly where the auxiliary electrode, sometimes called the counter electrode, comes into play.
Ah, the third wheel. So its job is basically to handle the current flow so the reference electrode doesn't have to. Like it takes the hit.
Exactly. Its primary function is to supply or accept the current that's needed for the reaction happening at the working electrode. It completes the main circuit path for the current, ensuring that essentially zero current flows through the high impedance reference electrode circuit. This keeps the reference electrode undisturbed, stable, and happy, maintaining its constant potential.
Okay, so it completes the circuit and protects the reference. And why do you often see these auxiliary electrodes being quite large, maybe made of platinum mesh?
Yeah, using a large surface area counter-electrode, often platinum mesh, is a really important practical consideration. The large area ensures that the current density, the current per unit area at the counter-electrode surface remains very low, even if the total current in the cell is significant.
Why is low current density important there?
If you used a tiny counter-electrode, the current density could become very high. This could cause unwanted reactions or large potential drops at the counter-electrode itself, which isn't ideal and can put a strain on the instrument controlling everything. Platinum is often used because it's relatively inert and a good catalyst for many reactions, and the mesh gives you huge surface area in a small volume, keeps things stable.
So we have this whole system: working electrode where the action is, reference electrode setting the potential baseline, and auxiliary electrode handling the current. It sounds like coordinating all this requires something pretty smart. That's the potentiostat, right?
That is absolutely right. The potentiostat is the sophisticated electronic instrument that acts as the conductor for this whole three-electrode orchestra. It's the brains of the operation. And yeah, it's vastly more complex than just a simple DC power supply.
How so? What's it actually doing that's so different from just supplying a voltage?
Well, it's designed for extremely fast response times and uses what's called a closed-loop feedback control system. It constantly measures the potential difference between the working and reference electrodes. Then it instantly adjusts the voltage between the working and counter electrodes as needed to force the working reference potential to be exactly what the user has set. While doing that, it also precisely measures the current flowing between the working and counter electrodes. And it can measure incredibly small currents down to microamps, nanoamps, even picoamps in some cases. It's all about precise control and sensitive measurement.
So it's constantly adjusting things to maintain that critical working reference potential. You also mentioned differentiating between applied voltage and compliance voltage.
Right. The applied voltage is the specific potential difference the potentiostat is maintaining between the working and reference electrodes. That's the value you, the experimenter, actually care about and set.
Okay.
The compliance voltage is different. That's the total voltage the potentiostat can output between the working and counter electrodes. Think of it as the instrument's power reserve or headroom. It needs enough compliance voltage to drive the required current through the entire cell, overcoming the solution resistance and any potential drops at the counter electrode while still maintaining the desired applied potential between working and reference.
So if your solution resistance is too high or your counter electrode isn't great, the potentiostat might run out of compliance voltage.
Exactly. It hits its limit. It can no longer force the working reference potential to the value you set, and your experiment essentially fails or becomes uncontrolled at that point. It's an important instrumental specification.
That clarifies it perfectly. Thanks. Okay, one last crucial piece, often added to the solution itself: supporting electrolytes. You mentioned them earlier. What are they and why are they so important?
Right, supporting electrolytes. These are basically an inert salt or acid, something like sodium perchlorate is a common example. You add it to your solution, usually at a much higher concentration than your actual reacting species. And the key word here is inert. It's chosen specifically not to react or interfere with the electrochemistry you're trying to study at the working electrode.
So if it's not reacting, what good is it doing? Why add it?
Its vital purpose is to significantly increase the electrical conductivity of the bulk solution.
Ah.
Why is that vital? Well, if your solution has low conductivity, maybe because your reacting species is very dilute, then as current flows, a significant and often unpredictable voltage drop can occur just across the bulk solution itself. We call this the IR drop.
So the voltage the potentiostat is applying gets partially lost, just pushing current through the resistive solution instead of all being focused at the electrode interface.
Precisely. This unwanted IR drop means the potential actually felt at the electrode interface is different from the potential the potentiostat is trying to set between the working and reference electrodes. It messes up your control and your measurements.
So the supporting electrolyte fixes this.
Yes. By adding a high concentration of this inert electrolyte, you make the solution much more conductive. This drastically reduces that IR drop, ensuring that almost all the potential difference the potentiostat controls is dropped precisely where you want it, across the electrode-electrolyte interface, within that tiny double-layer region. It effectively floods the solution with charge carriers that don't react, making it easy for current to flow without a large voltage loss in the bulk. It ensures your potential control is truly controlling the interface potential.
That seems absolutely essential for getting accurate data then. Does adding this electrolyte also affect the range of potentials you can work with, the voltage window?
It can, indirectly. Primarily, the voltage window is set by the solvent and the electrode material. In water, for instance, you're often limited by water splitting water, breaking down into hydrogen or oxygen at extreme potentials. While the supporting electrolyte itself doesn't usually change that fundamental window much, having good conductivity ensures you can actually reach those potential limits accurately. But yeah, extending the window often involves other strategies, like using specific electrode materials that are bad catalysts for water splitting, things like zinc, lead, or maybe mercury. These kinetically hinder the hydrogen evolution reaction.
Or, I guess, switching solvents entirely, moving away from water.
Exactly.
Yeah.
Using non-aqueous solvents is a very common strategy to get wider electrochemical windows, allowing you to study reactions that would be masked by water splitting. But every solvent still has its own breakdown limits, of course.
Wow. Okay, so we've really covered some ground today. We started right down at that nanoscale interface, the double layer, understanding it as this tiny, powerful capacitor. Then we saw the fundamental problem with simple 2-electrode measurements. You just can't know the potential where you need to, which led us to the elegance of the 3-electrode system, with the reference electrode giving us that stable baseline and the counter electrode handling the current, all controlled by the potentiostat. And finally, the crucial role of the supporting electrolyte, making sure our carefully controlled potential actually arrives at the interface we care about.
It really pieces together nicely, doesn't it? And connecting this back, this fundamental understanding, isn't just, academic. It's the absolute bedrock for designing better batteries, more efficient fuel cells, figuring out how to stop corrosion in bridges or pipelines, developing super-sensitive chemical sensors. It truly shows how mastering the microscopic, these tiny interfaces, leads directly to macroscopic technological breakthroughs.
It really does.
Yeah.
And it all hinges on understanding and manipulating those invisible forces right at that boundary. So, thinking about the immense electric fields we talked about, the precision control we can achieve, it leaves me with a question for you, our listener. What new and perhaps surprising electrochemical applications might still be out there, waiting to be discovered or radically improved, just by getting even better at manipulating these fundamental interfaces at the nanometer scale? What could be next in energy or medicine or environmental tech, driven by this deep dive into electrochemistry's foundations?
That's a fantastic thought to end on. A world of possibility still exists at that tiny interface.
Absolutely. Well, until next time on The Deep Dive, keep exploring those hidden worlds.